introduce himself and give you his background, a little bit about his background and everything, and we'll get started with Nutrient Cycles Part 2.
Thanks, appreciate it. Thanks, Rex. So thanks everybody for showing up. It's a packed room, thank God. Don't want to give a talk to crickets, but anyway, my name is Jesse Radolinski. I'm a postdoc in the lab of Tour, and actually I'm subbing here today for Tour. So all questions should be devoted and sent directly to this Twitter handle, not mine, the one under. Just kidding. There'll be an email. Yeah, I think I might have misspelled my email on purpose. I'm just kidding. So yeah, I'm a hydrologist, so I study water mechanics in the environment. I'm actually more, thankfully, in the role of soil, so I focus on the unsaturated zone. So basically everything from the water table up to the soil surface, to the surface of soil. That's kind of where I feel most comfortable. But luckily, I do have a background in soils, so I feel like I can give some of this information presented to you fairly well. So with that, I'll try to get moving. So today, this is the second part of the nutrient cycle, two-part series podcast. So we're talking about two very important nutrients, potassium and sulfur. And let's get moving. So we're gonna spend most of our time talking about potassium, and just a little bit of this time, the remainder of time, we're gonna talk about sulfur. But as some of you may know, there are some visual indicators of both deficiencies. You can see here the deficiency that you would see in a plant for potassium. It tends to be a little bit yellowing of the leaf surface, and then sulfur over here on the right tends to start more or less, from what I understand, at the more of the superficial leaves towards the top of the plant. But it's kind of a yellowing look in the plant. So yeah, so this is the distribution of how I'm gonna approach this next 30 minutes. Like I said, mostly potassium. Luckily for you all and for me, it's a lot easier to talk about potassium than it is for nitrogen, as I think you you guys had an idea of the other day. So there's a lot less going on in terms of the cycling per se, not so much dependency on these complicated redox reactions where we're giving and taking electrons, and we have to know the oxidation state of nitrogen and what's these intermediates. Is really kind of one or two forms of potassium that are useful in the environment for plants and for our understanding, right? So they got it simpler. There's also no gaseous form, so it tends to be solid or liquid. There's nothing flying around and off-gassing as like ammonium for nitrate, for example. So no weird mechanisms of loss that we have to worry about. And most of it's pretty soluble in the water, in the soil solution, and on the mineral surfaces. What's interesting is that, and we'll talk about that a little bit more, is it can be fixed into the minerals, which is an interesting mechanism, but we'll get into that. Different than P. So P is basically a covalent kind of bonding scenario where the phosphate, orthophosphate molecule really like has a chemical bond to the surface of the mineral, whereas potassium is a little bit different. And luckily with potassium, it's a really important nutrient, but it's not as huge of a deal for losses, at least from an environmental perspective, because it's not going to be poisoning anything. So there's not potassium poisoning going on. So we'll distribute the potassium between decaying soils, decaying plants, decaying fertilizer, and the potassium in manures and its solubility. So this is the general spread of the cycle. So here I have boxed in the sources. So for example, we have our inputs of fertilizer in our bag, what we call potash. We have down here on the bottom left, we have structural material that's bound to rocks. So the kind of parent material that forms soil, the rocks, this actually has a lot of structural potassium included in it. Most of this is not directly available for plants. And then we have a lot of potassium that's bound up in organic matter. I think maybe earlier talks kind of talked a little bit more about the importance of organic matter. Organic matter can kind of bind and hold on to a lot of materials. It's really important for the growth. No different here in the case of potassium, holds on to a lot of this nutrient. And we have, of course, animal manure as an input. And then we have these nice kind of interactions going on between the kind of immobile phase on the mineral, so that's the soil particles, back into the soil solution, which the plants access, and then, you know, in and out of the system. So our losses would basically be this kind of simplified erosion. So potassium has a fairly high affinity for soil, so you know it sticks on these mineral surfaces fairly readily. So it will, for example, bind these particles, and then you know if you have erosion problems, it's leaving to the system, to the soil. Uptake, you know, it's very water soluble and obviously very plant available. So plants are sucking this up like a sieve. So that's a loss from the box of the field, right? And leaching, right? So it has a high affinity for soil, more or less, but you know because it's very water soluble, because you know because natural processes below ground and water mechanics, it basically leaves the system by draining and leaching. Probably going to try to move a little quicker now. So K availability in soils. So what I said briefly in the last slide is that most of your potassium is actually, I think, what is it? 90 to 98% of all of the potassium is like bound up in the minerals. So the structural material that forms the rocks, that forms the soil eventually, that forms the clays, you know, potassium is an integral part of that structure. So, and it's not coming out readily. It takes time. It takes, you know, temperature, right? Warm. It takes thermal energy. It takes plant activity. It takes all kinds of time and interactions for this to come out, right? So then we have some basically we have, so I'm going to move from the one at the top left down to the top, to the one on the right corner. So the soil solution is where we can kind of, we can think about what the plants are accessing readily. So this is, of course, this is the dissolved material that's kind of moving around in between particles in the soil, the subsurface, and that's most available more or less to plants. So that's solubilized, it's floating around in the water. And of course, like I think you guys have probably heard enough about CEC and probably too much at this point, but similar scenario, there's exchangeable potassium sitting at the kind of clay interface surface. So there's potassium that's kind of like floating around the mineral surface that's that basically can also be plant available, right? So plants will knock that off, it'll come back out, they can take it up in a solution. And then we have an interesting mechanism where we call this trapped or fixed potassium, where so phosphorus, like I mentioned briefly earlier, has this mechanism where you have a very tight, very strong bond at the kind of hydroxyl groups of the mineral surfaces, and those become replaced, and then phosphorus and the orthophosphate bonds take the spot, the energy gap of that material, and it's really hard to break. So phosphorus is very immobile in a lot of scenarios, but potassium gets literally trapped. So it's like a physical entrapment in the mineral structure. So it's kind of like part chemical, but it's like also mostly a physical kind of interaction. So there's like these holes in the mineral structure, 2-to-1 clays, common clays, that can literally like hug phosphorus, or sorry, potassium. So a certain fraction gets naturally trapped in the mineral surface, and that's not necessarily available to plants. Soil solution K, so like I said, this is ready available for plant uptake. And this actually is a very small minority of the total K in the soils, right? This is like 0.1 to 2% of the total K. So nothing more than 24 to 48 pounds per acre. So like I said, moving still within the realm of plant available material, we have this kind of exchangeable potassium that's, you know, sitting around at the surface of the minerals that can be removed or exchanged and then readily available for uptake to plants. And of course, like any other dissolved material in solid and liquid phase. It's sitting at most of the time in an equilibrium. So there's not huge fluxes back and forth between the pool of water and the pool of the solid unless acted on by something else. So there's an equilibrium going on, and this is, like I said, readily available for plants. And important also, we're still looking at less than 1% of the total cable soils. Most of this is also is bound up in the minerals one way or another. This is what I talked about earlier. This is the fixed or trapped decay. Probably don't need to go into this in much more detail. Just know that it's not really exchangeable, so plants can't, spill out fancy chemicals into the environment and then replace it on the surface and then make it available to themselves for uptake. They have to, they rely on these more long-term processes to remove this. And yeah, again, this is still a small minority, 1 to 10% of K in the soils. And then the rest. So the bulk of this is kind of part of the structure of the rocks when they form. So this is basically a mineral component. It's not really coming out easy. Like I said, this takes a lot more input, energy, and working of the material to release it. So the vast majority, 90 to 98% of the potassium in your box of your field is bound up in the minerals. Like I said, pretty simple here. The 3 main loss pathways of your field is leaching. So if you can imagine, like I'm giving you the answer, but a simple scenario for a system that would lose a lot of potassium when you input would be a coarse textured soil that has a lot of room for movement of water and drains readily, and downstream basically you end up losing a lot of potassium, a lot of rainfall, right? I think most of you can kind of intuit the scenarios where you have a lot of leaching in your soils and in your fields. Then erosion, this comes down to, the management of the land, a lot of, I guess, loose practices with the surface retention of soil will result in a lot of potassium loss. And then an important one is crop removal, right? So the plants are consuming what's called this luxury consumption of potassium, so more than what they need, and it's every year kind of leaving with the crop from the field, depending on how it's managed, right? 3 losses. So this is just illustrating that luxury idea, luxury potassium. So on the y-axis, we're looking at basically the content of potassium in some kind of plant, right? On the y-axis, low to high, it's conceptual. On the x-axis, low to high availability in the soil. So this line splitting the axes is basically just showing you how the plants are accessing the potassium. And so at this kind of threshold, this is basically where we would draw the line for, this is how much plants would need for potassium. Above this line, plants are dipping into a pool of potassium that's in excess of what they need. So it's a luxury consumption. So above this line, we're kind of removing phosphorus from the system, and it's leaving, and it has to be replenished some way. So luxury consumption can mean the removal, the depletion of this material from the soil. So again, to reiterate, potassium is basically next to nitrogen, the most important macronutrient by mass, or by mass need. This other arrow is annoying. I keep saying phosphorus and potassium back and forth, so this is not helping. But focus on this arrow, potassium. So very important by mass and by proportion. It's the second largest compared to nitrogen for plant needs. And this is for a number of reasons. I don't feel like being that guy who reads every single point, but potassium is very important for a lot of plant physiological activities, right? It's an important component or activator of 80 different enzymes. You have, it's literally by mass, it's 1 to 4% of the dry matter. That's pretty big from a biological standpoint. It's really important for the osmotic regulation of plants, so it kind of helps plants respond to stresses, but just in general move material in and out of the tissues, right? So if you don't have potassium, you're not going to be able to perform basic functions. Yeah, very important. The slide's available. You can take a look at it later. And so this is a plot showing the uptake of potassium in, I think this is soybean over time. And basically this is supposed to illustrate how there's kind of a lull in the uptake early in the growing season, where there's really not much uptake of potassium going on, but then towards these kind of important growth phases, middle to late in the growing season, for example, in this period, the pod formation tends to suck most of the potassium out of the soil. So it's important to know that potassium uptake is not really, very wild until kind of mid to later parts of the growing season when the plants are coming to maturity. So this is important for how you time the application of the fertilizer. Yep. Similar story with corn. Mostly mid to late growing season, or it happens when we have these really intense physiological developmental stages. And yep. So an important thing to know for basically for your crop health is basically in the nutrient needs is that silage demands 5 times that of corn for grain, so that's a big number. Silage is a potassium sucker, and that's what the slide says. K deficiency. So this tends to result in shorter plants. So the leaf area index, I don't know if we covered that term earlier, but that's just kind of, it's the proportion of space covered by plants. It's kind of like a proxy of the canopy, so how much light is filtered out. Tends to be narrower and it tends to have shorter leaves. We tend to have delayed vegetative states. You could obviously drastically reduce your yield, increase the lodging, and you can have a lot of this purple stain in soybeans. So this is an interesting one. So there's kind of a dilemma with potassium, right? So basically, the idea is that if you don't apply enough, potassium, obviously you're going to take hits to your yield, 15 to 20% in this case, if you're applying a deficient amount of potassium. But then, of course, when you apply enough and you have a lot of yield, you suck a lot of this luxury potassium out of the field. So these have implications, I guess, for long-term kind of like sustainability of the nutrient budget, where kind of like a very productive field will deplete the nutrients over time, depending on how it's managed. So it's important to keep an eye on the potassium cumulatively through time, year to year to year field. This is probably, hopefully, still relevant number of distribution of potassium demand versus production in different parts of the world. North America is a heavy hitter when it comes to production. Still is. I checked yesterday. Should have updated this, but so basically we have a lot more production still in North America than we have demand, whereas the distribution is flopped in Asia. The demand is super high, several factors higher than the production means, whereas Eastern Europe is kind of similar to us in a sense, except less balanced. We have a little bit of demand but a lot of production, whereas Western Europe is, of course, super balanced with production and demand. So this is just a visual for you guys. So I'm not going to get too hard into these details, but basically so we refer to the potassium in fertilizers as potash, but in reality, this is not the typical potassium oxide. It's not a large component of the material that we add. We actually are mostly adding potassium chloride, but together we confusingly call these things a muriate of potash, which is supposed to be some way of standardizing the amount of potassium in your fertilizer material, which also confusingly dates back to the different ways people used to extract potassium from wood ash or potash. But it's just know that a muriate of potash is mostly, it's a way of standardizing the material based on the availability of potassium. So any given year, only about 20 to 60% of the applied potassium is taken up by crops. Why is this? Well, like I said before, there's a whole interesting ecosystem of interactions going on with potassium. There's potassium in solution, there's potassium that's kind of exchangeable on the surface of minerals. Then there's that weird squishing, fixing mechanism that's going on, and then there's even more immobile components of the large 98% pool of bound or mineral potassium. So in any given year, you have this kind of natural fluxing in and out of these different pools of materials. You might actually be taking relatively little of your new fertilizer inputs per year and actually tapping into this natural fluxing pool of potassium in and out of the minerals, in and out of the soil solution. So it's just interesting. If you were to trace the potassium going in, you may only be taking up 20 to 60% of that. How are we doing on time? Don't have a watch, but I assume I'm doing great. So this is potassium in manure. So basically, it's should be emphasized, I guess, that manure is an amazing source of potassium because a lot of the isolated fraction of potassium comes from an already liquid form of manure. So it's important to kind of when you're applying the manure, it's really that kind of liquid fraction that has the high potassium, but it's very plant available and very readily uptakeable when you apply it. So manure potassium is a very useful form of input. Wrong slide. So potassium, I basically just said this, the liquid fraction is very important for conserving this. So if you have, if all of your manure liquid is leaving the spreader or whatever, that's all of your potassium. Surface, so basically, so if manure is applied, so basically just when you apply your soil sampling is important for understanding what's the impact of the manure potassium. And like I said, it's immediately available once it's applied. It's basically considered a one-to-one with the K that you would get from your potash or fertilizer. So principles of smart management. So maintain, I guess like a lot of other scenarios, maintain the soil pH for your desired crop. Try to minimize how much soil is lost through erosion, and if you can, try to be smart with how you're applying your phosphorus based on the timing of uptake, right? Like we mentioned earlier, there's this idea of luxury consumption. We don't want to pull up too much. We don't want to deplete the phosphorus, or sorry, the potassium year to year, but also it may be smart to have a split application where we're applying a lot of our potassium later or mid to later in the growing season when the plants need it most, right? So take home the source. So the K in soils, basically the largest pool is that mineral component, whereas the amount that we're applying to the system is a relatively small fraction that's plant available. like I said, plants are using most of this potassium mid to late in the growing season during these kind of like buff sections of plant growth when you need it most. Silage is a huge sucker of potassium, 5 times that of the grain equivalent, and a myriad of potash. I don't think of those details, but all K is basically available, but quickly fixed into soils or leach. In terms of management, tests often, but maybe try to time the testing practically, around your application of fertilizer. Try not to deplete potassium over time. Don't allow the potassium to essentially be lost from the system year to year by this luxury consumption, if possible. And in terms of opportunities, we basically have soil sampling. Well, the opportunities are we can try to have a more sustainable year-to-year budget of potassium if we work towards it. So the last few slides, for some reason, we distributed this very little to sulfur, but sulfur is important, of course. Sulfur is still a macronutrient, and it's critical to a lot of plant physiological interactions during the growing season. So we'll start out by talking about how plants respond to an abundance or enough of sulfur. Basically, this is super important for protein synthesis, protein manufacturing. If you have sufficient amounts of sulfur in the plant, you're increasing the nitrogen efficiency of the system. So that's really important. Enough sulfur means that the system is using nitrogen correctly. And of course, the correct amount of sulfur in the plants basically can downstream mean improved animal nutrition, and also for us, right? Just alfalfa and members of the mustard and onion families tend to have a significantly larger requirement of sulfur. So back to the boxes and arrows. Sulfur is again, it's a little bit simpler luckily than the nitrogen cycling, but similarly we have a mineral component, an organic matter component. But one important point about sulfur is that a huge percentage of this is bound up in the organic matter fraction of soil. So your dark material towards the surface of the soil is holding on to 70 to 90% of your sulfur. So this is a little bit different from the potassium that we just talked about, right? This is coming like geogenic. It's mostly from the minerals, or stuck to the minerals in this case. That little bit of organic sponge is kind of holding on to most of our sulfur in the system. So, of course, if most of it's bound to organic matter, how does that become accessible to everything else in the plants, right? So some of this organic matter needs to be adjusted before we can access it, or before the plants can access it. So the mineralization is actually the breakdown of this organic material that's important for remobilizing or mineralizing this material so the plants can use it. So the kind of building of organic matter needs to be balanced by the mineralization of it, so like the freeing up of sulfur. So it has a similar physiochemical kind of mechanism that phosphorus does, that kind of covalent bonding at the surface, of pretty strong binding to soils, but it's not nearly as strong, and that comes down. Yeah, I don't want to get into it, but it comes down to the shared oxygen charge between the phosphorus and its 4 oxygen molecules. It's slightly weaker. Anyway, and then we have sulfate is still, it's a little bit, it still can form strong bonds at the surface, but it's still fairly readily leachable. So it's not like phosphorus in most scenarios. It still can be leachable under normal pH conditions. But it's nowhere near that of nitrate. Nitrate's like water, right? nitrate's very water soluble. And, people actually use nitrate from the hydrology perspective. They use nitrate as a tracer, like in some ways. People will just arbitrarily put nitrate, like they're doing an experiment or they're testing the loss of something, they'll put nitrate into water just to have something that's very mobile to see where the water's going. So anyway. Sulfur deficiency. So basically, it's this yellowing, I think, from the kind of upper parts of the plant, a pale green, lack of chlorophyll, and it's similar to nitrogen deficiency, probably in some ways tied to the fact, tied to how the plant uses nitrogen in general, right? So, like I said, it appears this kind of yellowing or pale greening of the plant starts from the top of the plant. Looks similar to the nitrogen deficiency, except for what I said, the nitrogen deficiency starts from the bottom and goes up. So it's kind of different physical distribution, but similar look. Yeah, so kind of, again, some of these things are a little bit intuitive in terms of where you might have sulfur deficiencies. You have a kind of very sandy soil that may not be great at retaining a lot of material, can lose a lot of phosphorus very quickly. Low organic matter, like I said, for sulfur, supercritical organic matter is holding on to a lot of your sulfur. So low organic matter can be an issue. Low pH, which increases basically the solubility of sulfate. So it can move a lot more from the mineral or from the organic matter. And cold, dry soils in the spring can delay release of sulfur from organic matter. So basically, why does sulfur deficiency happen? Some of these points are maybe more related to the past 2 to 3 decades, so not necessarily for nowadays, but after the Clean Water Act and after a number of regulations of air quality, we tried to reduce the amount of sulfur that was coming from coal, and, from a number of other emissions. So we used to have this natural deposition of sulfur from the atmosphere that actually, made the plants nice and fat and juicy with sulfur every year. It's not happening as much anymore, of course, which is nice. Air is cleaner, but it's not this extra added source of sulfur that was used for the plant. Changes in fertilizer, I guess, fairly recently have had repercussions for the amount of sulfur in the system. And again, similar to the mechanism I was talking about before, if we have higher crop yields, we can potentially year to year remove more sulfur from the field. And sulfur is relatively mobile. So, if you have a soil that's naturally very well drained, very coarse material, very high conductivity, you could potentially lose a lot of sulfur. Soil testing is not very successful. Sulfur has a similar behavior as nitrogen, and the main source of sulfur is coming from this pool of organic matter that's binding your sulfur. So again, the amount of organic matter in the pool is very important for sulfur as a nutrient, and routine testable can be useful, but not necessarily predictive. This is a chart. I'm not gonna go through it. Grain crops. This is detailed information for the application. So grain crops, 5 to 20 pounds sulfur per acre. Forage crops, 10 to 40 pounds per acre. When you expect a response. So I think we're close to the end. So take-home messages: keep an eye on the amount of sulfur in its system. This doesn't have the same distribution of uptake that the potassium did, but we still do have, of course, an increase in uptake as we go later in the growing season. So it's can be possible to split the application. That may be important for growth and retention. So manure can be a good source of sulfur, but if you can skip fertilizer, you're adding manure already. So it can be a nice substitute for the mineral fertilizer. Management challenges. Basically, it's the same depletion of sulfur levels in soils. Less atmospheric deposition than the past several decades can mean challenges for trying to maintain a sufficient amount of sulfur in the system. But we have opportunities for basically, we have regular testing and we monitor the deficiency of sulfur in the system. We can actually better regulate measure. So anyway, I think this is the end. So thanks everybody for sticking around. That's actually not my correct email. You have to remove the mail from the. So being honest. So, but still, you should email your Paul. Anyway, thanks everybody. Appreciate it. May not be able to answer.